Hi everyone, in today's video we're going to look into tracking any point method. We'll try to link concepts from the paper with pieces of code. So let's get started. So here's the paper, it's called Tapir, tracking any point with pair frame initialization and temporal refinement. So before jumping to the method, let's see what the method expects and what's the output. So given a video and a query point, the algorithms try to predict the 2D location in each frame of the video for the query point. It also attempts to predict 1D probability, OT, that the point is occluded in that particular frame, and 1D probability of the uncertainty of the estimated location. So given a video, which is bunch of frames, and a query point, the algorithm attempts to find for each frame, what is that query point? Is it occluded or not? And how certain are we about the location? So these three inputs are the output of the Tapir method. This is the GitHub repository for the TapNet method. It basically has more than one method, but the one we are discussing in this video is this one, Tapir, which represents this paper. They provide a number of Colab notebooks in this repository. We will be working on this one, the standard Tapir, because here they're saying we mainly report the results of the model in the paper. So this is the one they use to report the results in the paper. So we will be working on that. I copied that into my Google Drive. Here they use the original repository, but in the notebook that we'll be working on, I'm using my fork because I put some print statements along the way to see how the tensor changes its shape inside the code. I'm not going to share my fork because I'm afraid that I break something along the way. So it's not safe to share my fork. So let's connect. By the way, I'm using the TPU environment because this code uses JAX. There is a PyTorch version here where you can use the GPU environment. So let's install this repository. Here you can pick one of the two methods, Tapir or Bootstrapper. We're going to use Tapir. And here it will just load the checkpoints for the method that you picked. And now we are loading the checkpoint into parameters as state. It will be these are for the JAX model to load the weights. And we're going to download the video from this URL. This is the video. And here is the inference function. It defines frames, query points, and it adds the batch dimension for these. Here I'm printing the shape for the frames and query points, and it gets the output from Tapir, which we defined as Tapir model parameterized Tapir. It's this class here. This class here. So what we are doing here, we are creating an instance of that class into Tapir. Then we are feeding the frames, the query points, and the query chunk size to get the outputs. And in return, we are getting tracks where are these are the 2D positions of the query points, the occlusions, and the expected dist. This function here picks random points for the inference, and the inference is actually run through JIT. So the inference code will be passed through jax.jit, but for the first run it will be slow, but the following runs will be faster. So this would benefit us from the first run, because the first run where everything is just translated from uh, Python to Jasper, but all the following runs will be faster because the whole code is translated into Jasper. Here we can pick the size of the video and the number of points, the number of query points. So I'm keeping everything to the default. I'm not changing anything. So we're passing the height, the width, the number of points, and the frames will be the video resized, and the query points will be the sampled random points. Then we will pass everything into inference and get back the tracks and visibles and visualize all the points. Before I run this cell, let's just time it. I know we can time it from the code, but I prefer to do it this way. So here are the printouts that I've added to the code. I'll go and explain these one by one, but after we're getting the output. So it finished. It took almost 2.5 minutes, and this is the result. These are two moving query points. Other than that, they're all picked from the first frame. So these are moving with the object. So these are perfectly tracked. Anyways, let's see what are these printer statements and what do they mean and how the algorithm got to this point. So first we are starting with the frames. Frames is of dimension 1, 50, 256, 256, and 3. These are the number of frames. 50 is the number of frames. 256 is the height. 256 is the width, and 3 are the RGB channels. So these are 1, 50, 256, 256, and 3. The second one is the query points, which is 103. I'm using here 32 points, but this is the first dimension is the batch, second dimension is the number of query points, and the third dimension is 3, always 3. It represents the y and x coordinates on the image for the query point, and t the time, which frame this query point was picked from. So for each query point, we are passing the position and the time, the order, the frame order that query point occurred in. Then we're printing the get feature grids function. This one here, when you go to the call function. So this is a call function. There are 3 main functions. The get feature grid function, get query features, and estimate trajectories. So these are the three functions that will get the prediction, and the final prediction will be passed to the inference function that we just created. So the output of the first function, get feature grid, is 256 and 256, the refinement resolution, And the feature grid for 50 frames, we are taking the height of 32, the width of 32, and we're getting the 256 features. These are the resonant features from the backbone, and these are the height and width for each image. Then we are taking a different resolution with different features from the backbone. So we are taking two set of features, two different resolutions. They are calling these highs and lows in the paper. So what's inside get feature grids? So here we're passing the video and it's training, but it's the false because we are just doing inference. We're not training the model. And the refinement resolution. The refinement resolution, here I'm printing the refinement resolution. So the refinement resolution is 256, which means that we are not taking other resolutions. We are only taking the original resolution. So here the refinement resolution will, the resolution that we will be asking for features from the backbone. Here we are only passing one resolution from the print statement, which is 256, 256. I printed this here. Then I'm printing the feature grids and the highest features. We are getting these from the ResNet backbone. So this is the feature grid for all the frames and for all the points in the frames. Then we are getting the query features function. We are getting the higher query features and the query features. These are these printouts here, 128 and 156. These are the same features with these sizes. So these features for all points in the image, and these features for the query points. So the first one is the batch dimension, the second dimension is the number of query points, and the third dimension is the resonant features with the same dimension as the number of points in the image. So what these two functions are doing, the get feature function, it gets the features for all points in the image, and the get query features, it selects from those features, it finds the position for the query points and pulls them back, because the job of the algorithm is to match these and find the similarities. Now we're getting inside the estimate trajectory function. Inside estimate trajectory function, there are two functions: tracks from cost volume function, and these are the print statements, and the refine pips is done 4 times. 1, 2, 3, 4. I'll talk about the following statements today because I was so confused about that, but I'll talk about that later. So we are performing that tracks from cost volume once, but refine pips we are performing that 4 times. If you go to the paper, the method actually composed of 2 stages. The first stage is track initialization, and the second stage is called iterative refinement. So in the first stage, you're just getting the initial cost volume computed using relatively coarse feature map. So you are matching the query features with all features inside the image. So this is the cost volume, just to get an initial estimate for the position, for the occlusion, and for the uncertainty. Here is the estimate trajectories function, and here it calls the tracks from cost volume. It names it infer, but infer is basically a call for the tracks from cost volume. So here it gets the points, the occlusion, the expected dist, the initial values of that, and then it relies on the iterative refinement to improve the prediction. So inside tracks cost volume, it gets the occlusion from this neural net here. This is basically the mods here. is this one here. This is a neural net using the Haiku library. This is the first hidden layer, the second hidden layer, and the third hidden layer, fourth hidden layer, the occlusion output, and regression and convstats. So it pulls the occlusion, then it performs a nonlinear return occlusion, then it pulls the positions from the second hidden layer, then it starts to getting the occlusion from all the following layers, and it passes back the points, occlusion, and the expected dist. So this is what it retains. But these are the initial values. So these ones here in the figure are these ones here. We are starting the refinement with these values. So getting back to estimate trajectory, now we're getting the initial guesses from tracks from cost volume. Now we're getting inside the refined pips. Inside refined pips, we're passing the query points, the occlusion, the expected dist, and the pyramid, which is the cost between the features and the query features. So this is the CPU part, and this is the TPU part. This part here is getting the coarse pyramid and coarse chunked. In the paper, it was explained here in the iterative refinement. So here it is. The update is based on the set of locus core maps, which capture the query point similarity dot product to the feature in the neighborhood of the trajectory. These are computed on a pyramid of different resolutions. So for a given trajectory, they have the shape h prime times w prime times l, where h prime equals w prime, which equals 7. So in a 7 neighborhood, you are matching the query points and you are building a pyramid of that. So this is what is done here to get the coarse chunked. And then we are concatenating everything and feeding it into a neural net. So we are getting the position, the occlusion, the expected guess, MLP input, and coarse chunked. In the printout statements, these are the shapes of these tensors that we are concatenating and feeding into the neural net. So to explain these are the initial guesses here, points, the batch dimension, number of points, number of frames, and the location. Here is this tensor here. And for occlusion, for the number of frames, these are the 1D probability if the point is occluded or not, and the expected dist has the same size as the occlusion. For the estimated trajectory refined pips, the shapes of these tensors are the point guess is the batch dimension, number of points, 50 is number of frames, and 2 is the position in the image. The occlusion has the same size except for the last one because it's 1D probability. Expected guess is the same size except for the last one because it's 1D probability. And here are the new tensors, because we are familiar with these tensors because this was what we get from the initial guess from the tracks from cost volume. But these are the new ones, the MLP input feature and the cross chunked, these two here. So the first dimension is the batch dimension, second one is the number of points, third one is the number of frames, and 384 is basically 256 plus 128. So we are concatenating the features from the backbone along the channel dimension and passing this to the MLP for refinement. So if you go to the paper, you go to the appendix. Note that the version of the network with high resolution FQTI comprises both of high resolution 64 channel features as well as the low resolution 256 dimensional features, which are concatenated along the channel axis. So we are concatenating the high dimensional features and the low dimensional features. We are concatenating them into the channel axis here, and we are adding them together. So this is the MLP input feature tensor. The cross-chunked tensor, the first dimension is the batch dimension, second dimension is the number of points, third dimension is the number of frames, and the fourth dimension is the local neighborhood. So if you go to the paper, here they call them score maps, local score maps, and they have the size of H prime, W prime times L. And in our case, it's 7 times 7 times 2, which is 49 times 2, which is 98. So that's why we are getting 98, because we have two resolutions here. And for each resolution, we are taking the neighborhood of 7 by 7. So this is a 98. So these 5 inputs are fed into an MLP to get the prediction. So we're concatenating them into an MLP input, and we're feeding that into a network to get the prediction, the position update. At the end of the function, it will return the position update plus position guess, and it will add everything into the original guess. And this will be the output of the network. So in summary, the network takes initial guesses by matching the features, then it performs refinement to get the updated position, occlusion, and uncertainty. Now let's address why this has to be printed so many times. So here we have one track from cost volume and 4 refined pips, then one track from cost volume and 4 refined pips, and one track from cost volume and 4 refined pips, and the end we are doing that with only 4 at the number of points. So remember that we are passing 100 points, 100 query points, and we are passing into the parameters, we are passing the query chunk size is 32. So the algorithm splits the query points into chunks. Each chunk is of size 32. So that's why we are getting multiple runs for the estimate trajectory function. So we're doing it with 32, 32, 32, and 4, and the total of that will be 100 query points. So that's why we are getting this repetition in doing the estimate trajectory. I think they explained it in the paper why they. So here in the paper they're saying we found it was effective to run iterative refinement on only 32 query points per patch, randomly sampled at every iteration. So that's why our 100 query points got split into batches of size 32. So that's it for tracking any point algorithm. I'll make sure to complete this markdown file with the notes and links and a sample video. I'll make sure to complete that and share it with you guys in the description below. If you find this video helpful, please like and subscribe. Thanks for watching. Bye.